Okay, so I'll begin then. Um,
Guys, if you have any specific question from the last class, something which you want to ask, let's do that for next 2-3 minutes. You can chat or you can raise your hand. Omkar would promote you or he would get you in. So, have any questions?
yeah, all I'll say is it's important to have attended or reviewed what we did last time to understand what we will do today, because we are going to build on top of what we did last time, specifically um the part about what a derivative is. So
No,
I'm
guys, we
assuming,
are not going to discuss what derivative is. You have to go back to the last class. It is going to be a waste of time for everyone. Omkar, go ahead. You were saying something. I'll let you manage and we can start the class.
okay, so sure. All right, let me begin, and I'll do that by briefly just reviewing what we did last time. Take 5 or 10 minutes for that. So what we did last time was we began a study of, you can say, mechanics. Mechanics is, like I said last time, the study of motion, but really for the people who were developing the field, it was not just motion, it was really the study of change in general, because any kind of change in the universe, they felt, happens as a result of the motion of small particles making up matter, or um, including color changes, including any other kinds of changes, including in the human body. If they can be modeled, if they can be, if the motion of small particles can be understood, then we can essentially predict the future of the universe, because all we have to do is to apply the same equations, apply the same analysis to all the particles in the universe. And specifically, within mechanics, we began with the study of kinematics, which was the study of motion in the language of mathematics without worrying about what is responsible for the motion, without worrying about the cause. Okay, so kinematics purely studies the effects of those causes. Whatever causes motion, we don't care about it. All we care about is describing motion in an accurate way in the language of mathematics. Dynamics is what cares about causes. Kinematics is more about the effects of those causes. And within kinematics, we said that we're going to focus on motion along a single dimension or along a straight line first, because the mathematical tools that we would develop here, uh, specifically the basic tools of calculus, would then be extended to higher dimensions, where the uh, scenario is more complex in 2D or 3D. And as part of 1D kinematics, in order to model motion mathematically, we said that imagine a straight line. It could be either a horizontal line or a vertical line. Along that line, we are going to impose a number line or a one-dimensional coordinate system with some location as the origin. And if the line is horizontal, we could call it the x-axis. If the line is vertical, we could call it the y-axis. And along that coordinate system, we look at where the particle that we are tracking is, right? Because we want to describe the motion of a particle. Firstly, the word particle we mentioned is a point mass, so that its location is completely unambiguous. Otherwise, if you have something like an amoeba or an extended body, then it becomes confusing to describe where exactly is the location of that particle, of that object. So we look at point masses initially, and once we once we have a point mass, it's very clear what its position is. Its position is just going to be some x or y coordinate along the axis that we picked, right? It's going to be some real number. And since motion happens across time, we can represent time itself as um, as a separate axis with its own, you can say, coordinate axis, where the origin, which we would call as t equal to 0, is maybe the time instant where we start observing the motion, and then time flows forward. So any time instant is really a real number along that time axis. And so we can describe the position of a particle, whether it's x or y, as a function of time, because it's really going to change over time. So this is, we can say, a general function. So it's the position function, position of a particle at time instant t. Since the position is not fixed, we make it function of t. And then when motion happens, there is obviously a time interval over which it happens, and there is a certain change in the position of the object, right, which we call as delta x. It's always the final value minus the initial value. And this change in position is what we call as displacement. We saw that last time. So if it's negative, that means the final position is to the left of the initial position. So the particle is moving towards the left. If it's positive, that means the final position is towards the right of the initial position. So the particle is overall moved to the right. And the time over which this motion happened, we call that as delta t. And again, it's the final time instant minus the initial time instant. And this is what we call as the time interval. And if we had no other information about how the particle moved from its initial position to its final position, then we can just assume that it moved at a steady rate. And so we could look at the ratio of delta x to delta t and call that steady rate of motion as the average velocity. And this is how we defined it. And this definition assumes that the particle was moving uniformly. So again, if delta x is negative, then the average velocity will be negative. So if the average velocity is negative, it means the particle overall moved towards the left. If the average velocity is positive, that means the particle was on the whole moving towards the right. And this is the, you can say, the algebraic definition, but geometrically, this would simply mean the slope of the secant line, or you can say the chord line, joining the initial position to the final position, right? So now if you take the position axis and the time axis and you arrange them in a way that they are perpendicular to each other like this, and if you are tracking the particle at different positions, if this is your initial position, sorry, your initial position at the initial time instant and the final position at the final time instant, then this line, this red line represents that steady motion that we assume happened over the time interval. And the slope of that line, the rise over the run, would be, delta x. This green part is delta x. This yellow part is delta t. And so that the ratio of the green part to the yellow part would be the average velocity, which in this case is positive because you can see the red line is sloping upwards. If it was sloping downwards. Maybe the particle came down at some point like that. And if we measure the time, let's say between this point and that point, I mean the motion between those 2 points, then the slope would be negative. And that means the particle is overall moved leftward over this time interval. All right. Now, the reality is that average velocity is not a very useful quantity. Okay. The only reason why, it is introduced in 1D kinematics is as a stepping stone to talk about something a lot more useful, which is the instantaneous velocity. Because we saw last time that depending on where I pick the endpoint of this time interval, the average velocity values would all be different, right? So there's no way for me to say that this value is superior to that value and so on. But if we pick the time interval to be really small, that is, if we take this ratio delta x to delta t over a time interval that is really small, it's infinitesimally small, it's approaching zero, it's not exactly zero, but approaching zero, then we denote the deltas as small d's, and we call this as the instantaneous velocity at time t. This is the useful physical quantity that we are interested in. All right, average velocity was defined mostly as a stepping stone because the way you get the instantaneous velocity is by first taking the expression for the average velocity and then letting the time interval go to zero or approach zero. And geometrically, this was the slope of the tangent line at any time instant, right? So if I have an xt graph that looks like that, and let's say at this particular time instant, I'm interested in finding the average velocity. What I would do is I would look at the tangent line at this point, and its slope would give me the instantaneous velocity. Because what we do is we imagine taking the end point of that time interval and bringing it closer and closer and closer to the initial time instant. So we reduce this, and as we reduce this, what happens is that um, the average velocity is going to approach the instantaneous velocity, or this secant line is going to get closer and closer and approach the tangent line at that time. Right? And again, the sign of the instantaneous velocity tells us whether the particle is moving towards the right, as in this case, or towards the left. So if it went like that, then at this point, the particle is actually moving towards the left because you can see the slope is negative. The slope can also be zero, right? So at this highest point here, the slope is actually zero uh, because the tangent line is horizontal. And that means the particle is instantaneously at rest. Instantaneously at rest, right? That means its instantaneous velocity is zero. Now, this slope of the tangent line at xt uh, is what we can represent separately as a graph, and we can call that a graph of v versus t, right? And we can draw that graph below the xt graph in a way that uh, you can keep asking yourself, if I'm on a ski slope, I'm on a mountain slope skiing, then here the slope appears to be steep, then it's getting a little flatter, it's close to zero here maybe. Then it starts getting more steep in the positive direction. Then again it flattens out, it becomes zero. And then it starts becoming negative and so on. So we can, just by looking at these rough characteristics, we can come up with a crude VT graph. So here initially the slope is steep, so I'm going to make it, let's say, relatively high value, and then it flattens out, maybe it falls like that, and it becomes close to zero, and then it again starts rising up, and then it falls down to zero, and then it becomes negative, right? So I'm just drawing a crude VT graph, just following the shape. You just ask yourself, what's the slope here? Is it positive, negative, strongly negative? And based on that, you draw some kind of a crude VT graph. So you can get the VT graph from the XT graph uh, visually like this, although in a crude way. And so we say that the VT graph is the derivative of the XT graph, because it is derived from the XT graph in this way by successively taking the slopes at each point. Okay, so this is what uh, we did about velocity and time graphs last time, and we also said that um, along that turns around when the particle makes a U-turn, what will happen is that it's going to go like this and maybe turn around and then maybe go forward again. So overall, its displacement, its displacement or delta x value will be less than the actual length of the path that it walked, right? The total length of the path walked, assuming it's walking, and this total length of the path that it traveled is the distance. So we have to keep in mind that the displacement is purely defined as delta x. We don't care about what happened in the middle. All we care about is the initial and the final locations. Whereas in case of the distance, we care about the total length of the path that it took. And so if we could define the rate of change of motion based on displacement as the average velocity, we could define the rate of change of um, the location of the particle as, in terms of distance as well. So we could define a quantity called the total distance divided by the total time, but that would need to be given a different name. It would be the average speed. And why is it being given a different name? Because the average speed may not be equal to the average velocity, just like the displacement. Whenever the particle makes a U-turn, the displacement is going to end up being less than the distance. So dividing both by delta t, the average velocity in general is going to be less than the average speed, right? So as an extreme example, if a particle starts from this point, it goes there and it comes back to the same location. We saw that with a football player last time, who comes back to the same location on the football field. Then the average velocity, which is delta x by delta t, is going to be 0 because there is no change in the position over that time. But the average speed is not 0 because the player walked a substantial distance. And so dividing that by the time interval, we're going to get a positive non-zero value for the average speed. But if we make this time interval approach 0, it becomes so small that there is no scope for a U-turn. There's no scope for a U-turn if delta t is infinitesimally small. So in that case, the displacement and the distance kind of become the same thing. You can say that the displacement could have a negative sign because, if it's moving towards the left, it would have a negative sign. But the magnitude of the displacement would be the same as the magnitude of the distance if there's no U-turn. And I'll just write that down. The magnitude of the displacement will be equal to the distance if there was no U-turn during the motion. And when delta t approaches 0, this is always the case because any U-turn requires some time and we are not giving any time. We are saying our infinitesimally small time interval is, too short for a U-turn to happen. So what will happen is the magnitude of the instantaneous velocity in that case, just dividing that small displacement by delta t will be equal to the distance divided by that small delta t, which is the instantaneous speed. So in that case, the instantaneous velocity is the same as the instantaneous speed. And so this is always the case. This is always the case. But the average velocity can be, in general, less than the average speed, right? Unless there was a U-turn, uh, in which case the magnitude of the average velocity. So if there was a U-turn, the magnitude of the average velocity will be less than the average speed. If there was no U-turn, then the distance and the displacement are kind of the same, except that displacement might have a negative sign. And so the magnitude of the average velocity will be the same as the magnitude of the average speed. The magnitude of the instantaneous velocity is always equal to the instantaneous speed, right? But over a larger time interval, they may or may not be the same depending on whether or not there was a U-turn. So you have to be careful about, comparing average velocity and average speed. But instantaneous velocity and instantaneous speed always can be related like this. All right, so these are just some terminologies we are deciding and unpacking their implications. That's all. Nothing uh, deep in this as far as physics is concerned. We are just trying to develop um, a mathematical uh, quantity or multiple mathematical quantities that we think will help us describe motion. Right? How fast something moves, for example, that is something we have tried to capture, although we saw there are two different ways of capturing that. Right? Depending on whether you look at displacement or distance. Displacement is what we will prefer because it gives us a sense also of the direction in which the particle is moving, which uh, speed does not. All right, so this hopefully recapitulates and sort of consolidates what we did last time. I also did one thing. I defined the derivative using an algebraic formula, which is very important to remember. that since velocity, for example, is the derivative of position, I wrote it like this earlier, right? That v is dx over dt. Sometimes you will see it written as v of t is the derivative of x of t, right? Sometimes you will see it written like this, d by dt of x of t. These are all just different ways of denoting the same thing. All right, sometimes it might be denoted as dash, right? X dash of t. X dash just indicates that we are taking the derivative of uh, the function x versus t, right? So this is the notation used by Leibniz. This was the notation used by Newton. Newton and Leibniz developed calculus, and so their notations are different. The notation of Leibniz is what we normally study because it's more friendly. But the way we defined it was by taking delta x, delta x. So what is delta x? It's x final minus x initial. So if my initial time instant was was t and my final time instant was t plus delta t, then my initial position would be x of t and my final position would be x of t plus delta t, right? These two. And so delta x would be this divided by delta t, the time interval. If we take this ratio and we let delta t approach 0, this is the algebraic definition of the derivative. All right, so I'll just highlight this, that remember this limit definition of the derivative. You're cutting time into an infinite number of infinitesimally small time intervals and defining the instantaneous velocity at each of those intervals. And this is how you get all the formulas for the derivatives of all kinds of functions. So what we did is we used this, using this formula, last time we derived the derivatives for a bunch of, not too many, but maybe 2 or 3 examples. So for example, when x of t was the function t square, you might remember that we derived the velocity function as twice t. When x of t was t cubed, we derived this as 3t square. When x of t was t to the power n, I think that was the most complex calculation I did, we derived this as n times t to the power n minus 1. And I call this as the power rule. And what I want to do now is I want you to be able to take the derivative of any polynomial, right? And being able to differentiate. Differentiate just means to take the derivative of. Being able to differentiate or take the derivative of any polynomial function is something that we will do, because this is something you can do mentally. Once you get a little bit of practice, taking the derivative is like, how you remember a plus b squared is a squared plus b squared plus 2ab. You don't have to think about deriving that formula. In a similar way, taking the derivative is actually quite straightforward. Uh, uh, Once you get a little bit of practice. So I would say, my personal opinion is that the jump to algebra that you made in your middle school is actually a bigger jump than the jump from algebra to calculus. Calculus is not, uh, at least the calculus you learn in your high school. I know most of you have not taken math in 11th and 12th, but even those who have taken that, the level of that math in 12th grade is not, it's not something beyond the reach of, uh, it's not as hard as the jump you made from arithmetic to algebra. So function of x, sorry, any function of time here, because we are talking about the position time uh, function here. Any function of this form, let's say 3t square plus 6t plus 7. We call this a quadratic expression, as you might remember from your 9th grade, 10th grade math. So if you have a quadratic expression, maybe you might have a cubic expression where the highest power of t is 3, or you might have a quartic expression where the highest power of t is 4. The point is, for this function to be a polynomial, it must be of the form something, some constant plus something times t to the power 1 plus something, some other constant times t to the power 2 plus some other constant times t to the power 3, and so on, up to some finite, highest power of t, which we call as the degree of the polynomial. So this is a polynomial function, and for this we want to be able to calculate what the velocity is. Now I'm not interested in this specific function. I'm interested in a general polynomial. Looking at a general polynomial, I want that by the end of this class, you should be able to take the derivative, and in fact even answer questions based on taking the derivative. So we know how to take the derivative of t to the power n for any n, right? You just bring n down and you reduce the power of t by 1, right? So the derivative of t to the power 10 will be 10 times t to the power 9. The derivative of t to the power 99 will be 99 times t to the power 98. So hopefully this is easy to remember, and the proof of this was done last time. Now, suppose I know how to take the derivative of t to the power something. How do I take the derivative of, let's say, 3 times t to the power something? Let's say 3t square. Okay, so I'm just picking the first part of this. What if my function was just 3 times t square? Okay, I know that the derivative of t square is 2t. So what is the derivative of 3 times t square? Right? Or in general, what is the derivative of any constant c times t square? Right? So in general, if I already know that the derivative of, sorry, the derivative of x of t is, some function v of t, what's the derivative of c times that function? If I ask that question, how do derivatives change when I multiply the original function by a constant? Well, we can fall back to the limit definition to get the answer. So the derivative of c times x of t, think of c times x of t as a new function now. So what is the value of that new function at time t plus delta t minus the value of that new function at time t divided by delta t? That's what we'll do. So what's the value of this new function at time t plus delta t? It's just going to be c times x at t plus delta t minus the value of that new function at time t, which is basically this, divided by the time interval delta t. Now what I can do is I can just factorize out c because it's common to both the terms. And c is a constant. It doesn't depend on, it doesn't depend on time at all. So I can actually pull it out of the limit. So I could do it in 2 steps. That's more convenient for you. I first factorize it. And then I pull it out of the limit because it doesn't depend on t at all. X at t plus delta t minus x at t divided by delta t. Now, this limit is what I already know. I know that this is nothing but v of t. So this is just going to be c times v of t. All right, so this means if I multiply the original function by c, the derivative will also get multiplied by c. So then it's very easy to calculate this. If I know that the derivative of uh, t square is 2t, then the derivative of 3 times t square, the derivative of 3 times t square is just going to be 3 times the derivative of t square, which is 3 times 2t or 60. I think somebody mentioned 60. Right? I'm just picking the first part here, okay? So now we know how to find the derivative of uh, c times a function. We just find the derivative of the function and multiply it by c. Or we can say we can just push the derivative inside, like I did here. 3 times, take the derivative of what's inside. Um, okay, so now more examples. What's the derivative of, let's say, 60? What's the derivative of 60? It will just be 6 times the derivative of t. What's the derivative of t? Use the power rule. It's t to the power 1. So the derivative of that will be 1 times t to the power 1 minus 1 or 1 times t to the power 0. So it's just going to be 1. 6 times 1, which is 6. What's the derivative of a constant function like 7? And is just going to be a horizontal line at 7, right? Imagine a position time function like this. That means the particle is not moving at all. So what is its instantaneous velocity going to be? It's going to be 0. But algebraically also we can get this by saying what's the value of this function at t plus delta t? What is the value of the position at time t? Take the difference, then divide it by delta t. So clearly you see that the difference is 0. So this is clearly going to be 0. The derivative of any constant function is always 0. Okay, so hopefully you have like you see the uh, pattern here of how to find the derivative of c times something. Now the last piece that we need to figure out in order to be able to take the derivative of this entire thing is, so I know how to take the derivative of 3 times t square. I know how to take the derivative of 6 times t. I know how to take the derivative of 7. How do I take the derivative of the whole thing? Okay, so in other words, what is the derivative of the sum of 2 or more functions? Okay, so for example, suppose I want to take the derivative of uh, the first some function x1t plus some other function x2t. Okay, x1 and x2 are just names of two different functions. For example, x1 could be, 3t square, x2 could be 6t plus 7, or x1 could be something else. Normally in ninth and 10th grade, you would call these as f and g, right? F of x, g of x. Here, it's a little confusing because x is not the independent variable here, right? The position, the notation used for position is the x coordinate, which indicates the position along the x-axis. So x is actually the dependent variable here. Time is the independent variable. So that's why instead of using f and g, I'm just using x1 and x2. So what's the derivative of the sum of two functions? Again, we can fall back on the basic limit definition of the derivative and figure this out. What's the expression for the derivative? Well, I'm going to treat this whole thing as a new function. What is the value of this new function at t plus delta t minus the value of this new function at time t divided by the delta t? Right. So what's the value of this whole thing at t plus delta t? It's going to be x1 at t plus delta t plus x2 at t plus delta t, right? From this, I subtract the value of that whole green function at time t. So that's just x1t plus x2t, and I divide the whole thing by delta t. Now I can group together, I'm going to group this with this, and I'm going to group this with that. Okay, so I'll just regroup the terms here. Limit of delta t approaching 0, x1 at time t plus delta t minus x1t divided by delta t. Why am I grouping it like this? Because I want to be able to use the fact that I know the derivatives of x1 and x2 individually. And I know that d by dt of x2t is some function v2. So if I know how to take the derivatives of those individually, how do I figure out the derivative of their sum? So this is going to be x2 at t plus delta t minus x2t divided by delta t. Right? And now I can take the limits inside. Minus x1t divided by delta t plus limit. I mean, it's just saying the same thing. I'm just making it more clear that we are considering these two, we are splitting apart these two pieces and asking what does the first piece become as delta t approaches 0? Well, that just becomes v1t. That's the definition of v1t. And the second piece here becomes v2t. In other words, the derivative of the sum became the sum of the derivatives. So now we have everything that we need to take the derivative of any polynomial function. We know how to take the derivative of uh, any power of x, sorry, any power of t by the power rule. We also know what happens if we multiply a power of t by a constant. What happens to the derivative of the whole thing. And we also know what happens when we are taking the derivative of the sum of uh, two or more functions. Okay, if there were more than two here, if there were three or four, doesn't matter, we would do the same thing. We would have three or four such terms that we would split. We would still get the sum of as many number of derivatives as we have here. So now we are ready to ask what is the derivative of 3t square plus 6t plus 7? Well, the derivative of the sum of three functions. The way I will think about this is, well, I need to take the derivatives individually of these three pieces and then add them together. It's just the sum of the derivatives. So it's, let me make it more explicit. It's just the derivative of the first piece uh, plus the derivative of the second piece plus the derivative of the third piece. What's the derivative of 3t square? Well, it's 3 times the derivative of t square. The derivative of t square is 2t. So the derivative of 3 times t square will be 3 times 2t, which is 6t. What's the derivative of 6t? The derivative of 6t is 6 times the derivative of t, so that's 6 times 1, that's 6. We did that a few minutes ago. And what's the derivative of a constant? Well, that's 0. So it's just 6t plus 6. Okay, and with practice, you can actually directly write what the derivatives are. So let's say I take t cube minus t square plus 10t minus 100. Can you try this? What would be the derivative of this polynomial? All right. Priyanka and Akshada, Gulshan, Jyotsna, you all have some answers there in the chat box. So let's see, what's the derivative of t cubed? By the power rule, it's 3t squared. All right. What's the derivative of t square? It's 2t. Now this subtraction, see, subtraction is just addition with a minus sign, right? A minus b is the same as a plus negative of b. So the derivative of, if there was a minus sign here instead of plus, that doesn't make a difference because I would pretend that the function I have, the second function I have is minus x of minus x2 of t. So that's like multiplying x2 by a constant minus 1 in front. And I know the derivative of any constant times the function is just the constant times the derivative of that function. So that means the minus sign would come outside the derivative and I would just take the derivative of this. So that means the derivative of x1 minus x2 would be the same as the derivative of x1 minus the derivative of x2. So, um, so therefore the derivative of minus t square or t cube minus t square is the derivative of t cube, which is 3t square, minus the derivative of t square, which is 2t. And then I have two more pieces here. I need to add the derivative of 10t, which is 10. And then I need to subtract the derivative of 100, which is actually 0. So I don't have to add that in here. So 3t square minus 2t plus 10 is the answer to this. And you can do this mentally, right? With some practice, maybe practice 8 or 10 questions of taking the derivative, you will be able to basically do this mentally. So let's take an even longer polynomial here. 2t cubed minus 5t square plus 6t plus 10. Okay, I'm just making this up. Try to do this in 30 seconds. And if you can't, that's fine. You should get there after some practice. So try to aim that you should be able to compute the derivatives of polynomials like this in under 30 seconds. Just mentally. Should be able to write down the answer without necessarily writing any steps. Okay, so I'm seeing some suggestions here. Let's do this mentally, okay? What's the derivative of 4t to the power 5? Well, pull the 4 out. Take the derivative of t to the power 5. That's 5 times t to the power 4. So when multiplied by 4, so it's going to be 4 times 5 times t to the power 4. So that's 20 t to the power 4 minus 3 times the derivative of t to the power 4, which is 4t cubed. So 3 times 4t cubed is 12t cubed plus twice of the derivative of t cubed, which is 3t squared. So twice of 3t squared is 6t squared minus the derivative of 5t squared, which is 5 times the derivative of t squared, which is 2t. 5 times 2t is 10t. The derivative of 6t is just 6 times 1. And the derivative of 10 is 0. So this is the derivative. Okay. So this is what is expected of you, that you should be able to compute these derivatives very fast. Yeah, once you get practice, these will feel like easy peasy. It'll be like doing a plus b squared, right? That's how easy it would be. So, which is why, let's take this question from your problem set. Can you do this? So both functions are polynomial functions. A, B, and F are just constants. So you should be able to quickly take the derivatives. So velocity is something that as soon as you see velocity, you have to think of instantaneous velocity. So by the way, I didn't mention that before, but let me mention it here. Whenever the word velocity appears, is instantaneous velocity by default. Unless the word average is added explicitly, you have to assume it's instantaneous, because like I said, instantaneous velocity is the important uh, quantity. Average velocity is not important. Its only importance is in the fact that it appears within the definition of instantaneous velocity, because you first have the expression for average velocity and then you take the limit of the time interval approaching 0. Choice 4. Okay. So let's do this quickly. So find the velocity function of car P. So that's just going to be the derivative of AT plus BT square. The derivative of AT is just A, because remember A is a constant, and the derivative of T is 1. The derivative of BT square is B times the derivative of T square, which is 2T. So I'll just write this as 2BT. The velocity function for car Q is going to be the derivative of Ft minus T squared. The derivative of Ft is just F. The derivative of T square is 2T. So now we just have to equate these, right? So a plus 2bt is f minus 2t. So we have to solve for t here. So I'll bring all the t terms on the left and the constant terms move to the right. So that means t times 2b plus 2 is f minus a. So t is just f minus a divided by 2b plus 2, which you can write as twice of b plus 1. So that makes the fourth choice correct. Okay, any questions on taking derivatives of um, polynomial functions? If you have any questions, just raise your hands. Now, in a calculus course in 12th grade, you would learn to take the derivatives of many different kinds of functions, not just polynomials, but trigonometric functions, exponential functions, logarithmic functions, radical functions, rational functions, and um, uh, you know, we don't want to get bogged down by all that right now. We just want to understand the essential principles here, and it's sufficient to work with polynomials for now, um, to understand those principles and get comfortable applying them before we start looking at more, new kinds of functions. Okay, so let's just get comfortable with polynomials. I'm not sure if you're even expected to learn about other kinds of functions. Trigonometric functions you would need uh, to handle circular motion. So, but right now for 1D kinematics, we don't have to worry about it. No questions? Is this like pretty clear, like easy, or for how many of you is it new? Because I'm sure given the comfort level some of you are showing, you might already have learned this. But as such, for how many of you is this new? It's not new for anyone? Okay, well, that's good. Uh, all right, so let's look at something that hopefully would at least feel a little new. Uh, you would remember last time I mentioned how Aristotle uh, claimed that when you drop an object made of earth or water, all objects that are dropped fall at constant speeds, which are proportional to their masses. Right? This was the claim that Galileo had tried to refute by supposedly dropping two balls of very different mass from the top of the Leaning Tower of Pisa. Um, I want to deal with two separate claims here. Right? There is also this claim that objects fall at constant speeds. Now, this was something that was questioned even before Galileo. In medieval times, there were philosophers who pointed out that this needs to be corrected. Because think about the fact that if an object is falling at a constant speed, then if you jump off from a table and if you jump off from a high cliff, you should land on the ground at the same speed, right? But you wouldn't feel afraid of jumping off a table, but nobody in the right mind would jump off a tall cliff because you would get very badly hurt, if not killed. Right? So there were observations, common observations of this kind, right? If you drop a glass cup from a lower height, it might not even get cracked, right? But if you drop it from the top of a cliff, it might smash into pieces. So people did point out these simple observations. When you drop a stone onto muddy ground from a lower height, it'll make a hole in the ground. If you drop it from a higher height, it would make a deeper hole, right? Why is it making a deeper hole? Because it seems to be falling with a greater speed when it hits the ground. So it feels commonsensical then, based on common observations, to say that, well, um, the speed of an object that is dropped is not remaining constant as it falls. This applies to objects made of earth, and it also applies to objects that are liquid. When you open, let's say you open the tap in your bathroom, right, allowing the water to fall sufficiently from a sufficient height on the floor, what you will see is that near the mouth of the tap, the flow seems continuous. But then, as you look closer to the ground, you'll see that the droplets separate out, right? So why would that happen? Well, if the droplets are increasing their speed as they are following, then they're going to separate out, because the droplets further up are falling at a lower speed, the droplets further down are moving faster and faster. So the 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 s- the continuous fluid is going to get broken up into uh, separate pieces, right? So this is based on these observations, we can say that let me add, but so so velocity appears to change with time. So velocity of a falling object appears to change with time, right? Specifically, we can say that the speed increases with time. Speed of a falling object increases with time. All right. Regarding the so I'll just also point out one other thing. Objects fall at a speed proportional to their masses. Well, even if Galileo didn't actually do that experiment from the top of the Leaning Tower of Pisa, um, uh, we don't know if he did it. Many historians say he actually didn't, because he felt that he had a strong proof that this is impossible. And his proof went something like this. If objects, so firstly, objects seem to accelerate. When I say accelerate, I mean their speed seems to increase as they fall, right? This is something that people argued even before Galileo, based on these common observations. The other thing is that um, objects of different masses seem to fall in the same manner. Uh, and and as a simple proof of that, this was a thought experiment, right? One of the most beautiful thought experiments that you can encounter in science. Again, not mentioned in your textbook, so I'll just give you a brief description of what it's like. So Galileo said, okay, here's the proof for how objects of different masses cannot fall at different speeds. There'll be something contradictory. So consider an object that is a composite object. Okay, it's made of a 1 kilogram piece and a 10 kilogram piece. Okay, it's bound together and you make it fall. Okay, now what you do is you tie them with a string so that if they separate out, um, eventually, what did Aristotle predict? Aristotle predict that they would separate out because the 10 kilogram mass would fall at a higher speed. So that means the string that is tying them together would become stretched. It would become like this. Right? It would become like this as the object falls. So the 10 kilogram mass is trying to fall at a higher speed. And so what it will do is as it tries to fall with a higher speed, it is going to pull the 1 kilogram mass downward to make it try to fall a little faster than its natural speed. And the 1 kilogram mass is trying to fall slower than the 10 kilogram mass. So it's going to try to pull the 10 kilogram mass slightly upward so that it falls with a somewhat lower speed than its natural speed. So according to Galileo, the speed of fall must be intermediate, must be intermediate between the natural speed of the 1 kilogram mass and the 10 kilogram mass, right? Because the 1 kilogram mass got pulled downwards so that it's falling a little faster than its natural speed. The 10 kilogram mass is being tugged upwards, so it's going to fall at a somewhat lower speed than its natural speed. So the speed of the combination should be intermediate between the natural speeds of the 1 kilogram and 10 kilogram mass. Now Galileo said this is a contradiction because if we had never tied them with a string, suppose we had just glued them together. Okay, I just glue together these two so that this is effectively a mass of 11 kg. Should fall with a natural speed that is more than the natural speed of a 10 kilogram mass. So effectively what we have is a contradiction. This is a logical uh, contradiction. How can both of these be true? There's something wrong, um, some wrong assumption that we have made, which is leading to this contradiction. And what is that wrong assumption? Well, the assumption that we started with, that when an object is dropped, it falls with a uh, with a speed that's proportional to its mass. Right? This was Galileo. Galileo was proud of the fact that one could do math and apply logic and conclude things about the physical world without having to do any experiments. Right? Without having to do any experiments, one could prove that Aristotle's um, view here simply cannot be correct. Right? So there really wouldn't have been any need for him to do that experiment from the top of the leaning tower of Pisa. But that's the story, at least, that he did it. Um, anyway, so the point is there are two issues in this claim. One is that objects fall with a speed proportional to their mass, which I just showed you, the contradiction that results if you assume that. And the second, which seems contradicted by observation, is that they fall at a constant speed, which is also, you know, contradicted by uh, common observations of the kind we discussed. So when we look at free fall motion, different masses must be falling at the same rate, and their speeds should increase over time, right? Any kind of mathematical modeling of free fall motion should account for this fact that the speed of a falling object increases over time, right? That is, velocity of a falling object appears to change with time. And if velocity changes with time, then it makes sense to talk about the rate of change of velocity, right? To define a new physical quantity which mathematically captures the rate of change of velocity. Now, just as velocity itself was captured by defining it as the rate of change of position, rate of change of position, we can define a new quantity as as the rate of change of velocity and give it a name, the rate of change of velocity dv by dt as a new quantity, which is namely the acceleration. So one thing you will note, therefore, is both velocity and acceleration are defined as derivatives. So you understand now how essential mathematics is to physics, because the very definition of these two physical quantities is as the slopes of the tangent lines of the xt graph or the vt graph in this case. If we try to interpret dv by dt as acceleration, that means if Sorry, did I get cut off? I don't know how. I think I got cut off for a few seconds. I'll just share this again. So acceleration as a function of time is being defined as the derivative of the velocity function. So it's the same definition we are going to use. Find delta v by delta t and let delta t approach 0. Right? So how do we find delta v versus delta t? Well, you find v of t plus delta t and subtract v of t from it, and you have delta t here. All right, so this is the quantity that we call as acceleration. Now, if you want to be nitpicky, you can give this quantity a name, right? You can call this the average acceleration. And you can say, well, this is the instantaneous acceleration. And that's fine. But really, the average acceleration doesn't really have much importance in physics. It's the instantaneous acceleration that we care about, because things can change from one instant to another. right? So this is how we would define the instantaneous acceleration. Now there is another notation here. Since d by dt of vt can be written as d by dt of vt itself being being written as d by dt of xt, right? So it's the derivative of the position function. So we call this, we often denote this as d square by dt square. Okay, and this is a terrible notation, but understand that when we are not squaring anything here. Okay, we are not squaring dt here, we are not squaring any d here. All that this means is this is the second derivative of xt, or think of this as the rate of change of the rate of change of xt. All right, so just as a trivial example, if xt is t square, what was vt? Vt was the derivative of xt, so it would be 2t. Now what would be the acceleration function if vt is 2t? Well, we take one more derivative. We take the derivative of v of t with respect to time, and that would just be twice of the derivative of t, twice of d by dt of t. So that's just 2 by 1 or 2. So if we can go from xt to vt, we can go from vt to at. In fact, we can go from, we could define a third derivative of position if we wanted to. We could define a fourth derivative of position, fifth derivative of position. We can keep defining as many terms as we want, right? As many new quantities as we want, simply by taking one more derivative, right? But we don't do that because when we learn dynamics, we realize that it's sufficient uh, to stop at acceleration, because the third derivative onwards don't really have much use for us in explaining motion. So we just stop here. Now, if acceleration, um, so in this example, acceleration was constant, right? So constant acceleration is also called as uniform acceleration. Just like constant velocity, motion at constant velocity is called uniform motion. Motion at constant acceleration is called uniformly accelerated motion. It's not motion at constant velocity, it's motion at constant acceleration, uniformly accelerated motion. All right. So so what does it mean for acceleration to have a negative sign, right? It's possible that when we take the derivative of v of t, we'll get some magnitude for the acceleration, but it also might have a sign, positive or negative sign. We know what it meant for xt to have a positive or negative sign. Negative sign just means the displacement was towards the left. When v of t had a negative sign, it just meant the instantaneous velocity is towards the left. That means the particle is moving leftwards. What does it mean for acceleration to be negative? If a is negative, that means acceleration is towards the left. Okay. Now, acceleration is not something we perceive when you see a moving particle. We can make out whether a moving particle has a high speed or a low speed, uh, intuitively, you know, just you know, seeing whether a car zips past really fast, we get a sense of whether, whether it went past fast or was it slow. And of course, we see the direction in which it's moving. So velocity is something we can roughly make out, not the numerical quantity, but at least a judgment about whether it's fast or slow and its direction. But acceleration is not something that we can normally make out. So if acceleration is towards the left, there are two options. It is possible that the velocity could be negative. Velocity is negative. It's also possible that the velocity could be positive while the acceleration is negative. So if the velocity is negative, that means the particle was already moving. Sorry, pen is creating trouble here. Particle was or is moving left. And if the acceleration is towards the left, that means it's going to speed up. Will speed up, okay, as it's moving left. If the velocity is positive, that means the particle is moving towards the right. And what does it mean for the acceleration to be negative? That means dv by dt is negative. So if dv by dt is negative, that means in the vt graph, you're going to see v come down. So that means it's going to slow down. So we can say in general that when v and a are in the same direction, particle speeds up. When v and a are in opposite direction, the particle slows down. And this slowing down, there's a term for this. You can call it deceleration. Sometimes it's called as retardation. Basically, it means the acceleration and velocity are in opposite direction. It does not mean that acceleration is negative. Okay, keep that in mind. When a particle is slowing down, it doesn't mean acceleration is negative. It just means that the velocity and acceleration are in opposite direction. It's possible that the velocity could be in the negative direction and the acceleration could be in the positive direction. Even in that case, the particle will slow down as it's moving to the left. All right. All right, so we've defined this new quantity and hopefully we've got some sense of what acceleration is. Deceleration. Jyoti, you had a question about deceleration? So deceleration, retardation, these are just names for slowing down, but we will just stick to the name acceleration. Okay, but remember that acceleration being positive or negative has nothing to do with whether the particle is slowing down or not. Whether it's slowing down or not depends on whether the acceleration and velocity are in the same direction or in the opposite direction. Anyway, so going back to that scientific issue, how do objects fall? Okay, now we know that they fall with increasing speed, and uh, that rate of fall is actually Okay, that interruption happened again. Are you able to hear me? Network problem. Did you also get logged off, or am I the only one getting logged off? Okay, everyone's getting logged off. Okay. Yeah, not sure why this is happening, but anyway, going back to the screen. Okay, so this is the issue that, you know, Galileo was curious about. He already knew that, you know, things speed up as they fall, but is that and is that uniformly accelerated motion, or is the acceleration itself non-uniform? So how do you tackle that question? I'll write that question down. Is free fall motion an example of uniform acceleration or not? Okay. So I'm going to, we are going to, we have enough tools now to be able to um, answer this, or at least design an experiment that could answer this. Uh, I will describe the analysis here in the language of calculus, although Galileo did not have calculus. He did it in a more indirect way, but the essence of his analysis was similar to what we are going to do. If, okay, if acceleration is uniform, let's say an object is falling with uniform acceleration, that is, a is some constant, okay? Given the fact that a is the derivative of v, what should the function v look like? Think about the inverse problem now. Okay, we know how to take the derivatives of polynomials. After taking the derivative of some function, we got a constant a. What should that function have been such that after taking its derivative, we are left with just a single constant a? What do you think? What sort of function will leave a derivative of a constant? Jyoti, you mentioned modulus. I'm not sure what you mean by modulus here. Um, think back to, look at this. Okay, we have a bunch of functions being added, subtracted. Which of, what sort of function gives rise to a constant here when you take the derivative? Exponential, no. Um, we actually haven't looked at exponential functions, but exponential functions don't have constant derivatives. In fact, the graph of an exponential function goes up much more rapidly than, say, quadratic or cubic functions. So when you take the derivative, the slopes are not going to be constant. They're going to increase, uh, even for derivatives. Sorry, even for exponential functions. Variable to the power 1. Okay, someone said variable to the power 1. So if you focus on let's say this part 60, that left a constant 6. Right? In fact, even a constant function like 10 would leave a constant 0 that we don't see here. Right? So in general, if I tell you that the result is a constant, it could have come from a linear function. A linear function is what will have a constant derivative. Does that make sense? So if the acceleration is constant, that means the velocity must be of the form at plus b, all right, a linear function of time. Why is that? Because if you take the derivative of this linear function, I'll get the a. So the a must be stuck to time because derivative of this needs to produce a. So a must be stuck to time, and this there could be an extra constant b which gets eliminated when we take the derivative. Okay, so v of t must be a linear function of t. Now, if a is my acceleration, I know what this a is. I know t is time. What is this b? If if at all there is a b in the velocity function, how can I find out what b is? Well, notice one thing, that if I put t equal to 0 on both sides, I'm going to get v of 0, the velocity at time 0 is a times 0 plus b, right? This means my b, by the way, here I should say velocity at t equal to 0. Okay. Because a times, I don't want you to think that this is acceleration at time 0. This is acceleration times 0. We make that explicit. This is a times 0 plus b. So that means b is my velocity at time 0. Right? I can denote it like, maybe I can denote it like this. And I can call it initial velocity. If acceleration is constant, my velocity function, therefore, must be of this form. Some initial velocity plus acceleration times time. Right? If a of t is a, then v of t must be of this form. Okay. Everyone agrees with this? This is a linear function, right? Notice that okay, let me also show this graphically. If a of t is constant function, let's say it is this, at some constant value a, I'm sort of misusing the variable letter here, but just think of this as some constant, okay? If I were to draw the velocity time graph here, we say a of t, just to be clear, it may start with some velocity v0, and it will have v of 0 plus at means it's going to be a linear function like this. Okay, that's what this is, like y equal to mx plus b, the slope intercept form of a linear equation. So y value is, mx plus b or mx plus c. I don't know how you remember it there, but a is the slope of the line, and v0 is the y-intercept, or in this case, the v-intercept. Okay, so this a is nothing but the slope of this line. And it's positive, a is positive here, so I've shown it as a positive slope. If a was negative here, it would be a constant horizontal line below the origin. And in that case, my slope would have been negative. Okay. So this makes sense. This is what the math is leading to, right? I'm not even looking at anything outside the world, outside in the external world right now. I'm just saying if the rate of change of uh, velocity is constant, then the velocity function has to be a linear function with v0 being the initial velocity and a being the acceleration. What about, okay, let's go one step further and say, now if v is this, what is the form of xt going to be? I want a function xt which, after I take the derivative, when I do dx by dt, I should get a function that is linear. After taking the derivative, I should get v0 plus at. What sort of function is xt going to be? Okay, I want after taking the derivative a constant to be there, specifically v0, and I want a linear term also, which is at. What should be the form? What sort of function is xt going to be? Again, think back to what we did here. I want a function that after taking the derivative leaves maybe a constant expression and a linear expression. Well, it's very clear that these three terms are the portion that produce a linear derivative, right? A quadratic expression which um, produces a power of 1 here for t, because from the original degree 2 term. So this 2 will become 1, this power of 2 will get reduced to 1, and this power of 1 will get reduced to a power of 0. And maybe there was some extra constant there which completely disappears. Okay, so the point is that xt is going to be some quadratic expression. Now we need to figure out what exactly that quadratic expression is, which we'll do on the next page. All right, so what I want is, suppose xt is at square plus bt plus c. Okay. In that case, the derivative of xt is going to be something times t plus b plus 0, right? Now, what do I want it to match? I want it to match v0 plus at. So that means this part must be v0 and this part must be a times t. Makes sense? So I can come up with an expression for xt which will give me exactly v0 plus at. If I choose my capital B here, the coefficient of t to be v0 and the coefficient of t square um, to be what? Coefficient of t square is a, but I know that twice of that capital A should be my small a, so I need to pick a coefficient of t square which is a by 2, and moreover b has to be v0. Okay, so my xt therefore is going to be a by 2 t square plus v0 t plus some constant c that I still don't know. I still don't know what c is, but I figured out what a and b should be so that I get exactly v0 plus at. Now I'll do the same thing that I did here, which is figure out what this constant is by just looking at the initial conditions. Right? So if I just look at what's happening at t equal to 0, at t equal to 0, I have x of 0 on the left side, the position at t equal to 0, right? x0, which is the initial position. Initial position is going to be equal to, according to this formula, on the right side, I have some 0 plus c. So that means my constant c is nothing but my initial position. So that means my x of t is going to be x0 plus v0t plus half at squared. So I can finally write my xt is x0 plus v0t plus half at squared. So here's the thing. If my acceleration is constant, then my velocity function should look like this, and my position function should look like this. And I'm not doing any physics here. I'm just saying the math is the differential uh, calculus that we looked at so far. That is itself pointing me to this. Any questions about this? This is the prediction from, if any motion that's uniformly accelerated must have velocity and uh, position functions which vary like this. So this now points us to an experiment that we could do to determine if free fall motion is actually uniformly accelerated. Because what we really can measure, at least with crude instruments, as an object falls, is its position over time. We imagine a video camera recording the motion. What we see, what the camera sees, is really the position, and it's recording the passage of time. So x versus t is what it gets. So, by the way, another way to write this is xt minus x0 is v0t plus half at square. Xt minus x0 is just the change in position, or you can say the displacement. This is the displacement, v0t plus half at square. Now, here is how we could think of a simple experiment. Design an experiment to test if delta x varies with t in this way. What would a simple experiment look like? Well, choose an experiment where your initial velocity is 0. So v0t is anyway wiped out, right? Test if the displacement, which is really in free fall motion, the amount by which an object falls, is half at square. Now, a, of course, we don't know, uh, but we could test if delta x is proportional to t square. The displacement being proportional to t square, assuming you start out with 0 initial velocity, would be a test of whether free fall motion is actually uniformly accelerated. So what did Galileo do? This is the kind of experiment that he had to set up. So if delta x is proportional to t square, right now what we have done is we know delta x would be half at square. right? So in 1 second, um, the delta x would be some half a, that's the amount by which the object would fall. In 2 seconds, delta x would be, t square would be 2 squared. So 4 times that, right? 4 times half a. In 3 seconds, delta x would be, 3 square times half a, 9 times half a, right? And so on. So basically the displacements, ratio of displacements after 1, 2, 3 seconds would be 1 is to 4 is to 9 is to 16, that would be the ratio. That's something we could check. Uh, another way to, an equivalent way to do this is look at the the displacement during the first second, during the second, and so on. So displacement during the first second is half a, right? The displacement during the second is going to be what? It's going to be 4 times this minus this, right? We are looking at the displacement from t equal to 1 to t equal to 2. So that would be 4 times this minus 1 times this. That would be 3 times that. 3 times half a. The displacement during the third second would be what? 9 times this quantity minus 4 times that quantity. That would be 5 times that quantity. So the ratio of displacements during the first second, the second, the third second, and so on would be the ratio of the odd numbers 1 is to 3 is to 5 is to 7 is to 9 and so on. This is what Galileo saw. Okay, Galileo verified this with experiments. Now, free fall was too fast for him. So what he did is he slowed down free fall motion by using an inclined plane. So what you do is um, you have an object that is a particle that is freely falling, but its motion is slowed down because it's coming down a ramp instead of coming, falling vertically down, which was too fast for Galileo to measure. So what he did is, um, well, there are two ways you could do this, right? One is to mark lengths that are in this ratio on the inclined plane, right? Lengths that are successively in this ratio. So maybe this is one, this is the next 3 part, this is the next, oops, that's the next part, which is supposed to be of length 5, and so on, right? 1 is to 3 is to 5, and check whether in the first second, after the first second, the ball is exactly there. After the second, the ball is exactly here. After the third second, the ball is exactly there, and so on. Or alternately, check where the ball is after the first second, measure that length, check where the ball is after 2 seconds, measure that length, I mean that total displacement, measure where the ball is after 3 seconds, measure the total displacement there, and verify that the ratios of those displacements are 1 is to 4 is to 9 and so on. This is what Galileo did. And verified these ratios. showing that free fall motion is uniformly accelerated motion. So it's the design of the experiment is based on the mathematical predictions here. Mathematical prediction that the position or the displacement versus time must be a quadratic expression. And so you set up an experiment where you verify that the increase in the displacement is a quadratic function of time. Okay, you don't just set up random experiments. You have to plan it in a way that is verifying a specific prediction that you're making. If acceleration was itself varying with time, we would not have this relationship, right? We would not have this relationship between displacement and time. For example, if acceleration was itself, uh, just for argument's sake, if acceleration was itself a linear function of time, then the velocity function would be quadratic, so that when you take the derivative, you get something linear. So the velocity function would be a quadratic function of time, which means the position function would have to be a cubic function of time, so that when you take the derivative, you get a quadratic function. And if the position function is a cubic function of time, then the displacement would actually be a cubic function of time. So what you observe then through experiments on free fall would not be ratios in, would not be these exact ratios. There would be some other ratios. So that numerical precision in the predictions is crucial for verifying that free fall motion is uniformly accelerated. So therefore, for uniformly accelerated motion, and by the way, I should put this in as well. So the xt versus t graph is going to be of this form. X0 plus V0t plus half AT square. So you remember from your quadratic equations that uh, the graph of this is a parabola that will either open upwards or downwards depending on the sign of the coefficient of the highest term here, a. So let's say acceleration is positive here, so mm, maybe the particle starts from x0 here, and its graph might, so velocity is increasing with respect to time. All right, so the initial slope is positive. Um, so that means my xt has to already be going up like that. Okay, so that when I take the derivative, my initial slope is already positive. Okay, and this is basically a piece of a parabola. So let's see. So therefore, for uniformly accelerated motion, we have two equations already. Where a is constant. We know that the velocity is going to be in general v0 plus at, right? Velocity at time t. Okay, basically we are talking about this. V of t is the same as v. And the position as a function of time is going to be, you can say, given by this. The displacement is v0t plus half at square, or we can write this as x of t is x0 plus v0t plus half at square. do the same thing. Now, we can actually combine these two equations and eliminate time. So delta x is v0t plus half at square, right? So what if I take out t common here? And I get v0 plus half at. Sorry. Now, so how do I eliminate time here? I could calculate time from the first equation. It's v minus v0 by a. And I could substitute it here. Substitute it into this. Substitute time as v minus v0 by a into this. So I get v minus v0 by a times v0 plus half a times v minus v0 by a. All right, I'm just substituted v minus v0 by a for time. I see cancellations here. So I'll get v minus v0 by a times v0 plus half v minus half v0. Right, and if I combine v0 and minus half v0, I'll get half v0. So I'll get half v plus half v0. So in other words, v minus v0 by a and half v plus half v0 is just another way to write it is v plus v0 by 2. Now I can use a minus b times a plus b is a square minus b squared. Right, that basic result from your earlier algebra. So v square minus v0 squared is 2a. And if this is to be equal to delta x, that means v square minus v0 squared must be 2a times delta x. Or we can say v squared is v0 squared plus 2a times delta x. This is a third equation that is independent of time, that doesn't have time in it, which is many times useful. The first two equations, though, have all the information. The third equation just follows from the first two. And the first two equations just follow from pure math, right? Just from the definition of acceleration and velocity and from the assumption that acceleration is constant, you get these three equations. The first two equations and then the third by just combining them and eliminating time. Sometimes there is a, fourth equation. This is not very important for the average velocity. So average velocity, when you have uniformly accelerated motion, is going to be what? Well, the definition of average velocity is it's delta x by delta t. Now delta x is v0 t plus half at square, right? And delta t is actually t because we are measuring time starting from t equal to 0. So delta t will be just whatever time instant, final time instant t we are currently talking about. So it's just going to be this divided by t. So it's just v0 plus half at. And if you plug in again the fact that t is v minus v0 by 2, sorry, a, v minus v0 by a, the same substitution we did previously, we'll get v0 plus, a cancels out, v by 2 minus v0 by 2, um, So that means my average velocity is basically the average of the initial and the final velocities. Okay, so sometimes this is also assumed, or sometimes it's helpful, less often though. The first three equations are most common. Another equivalent way of writing this is, delta x is v average times delta t. So we can just say delta x is the average velocity times delta t. So these are the three equations. Fourth equation is not as important, but the three equations that come in very useful in 1D kinematics. And if you look specifically at free fall motion, which is a special case of uniformly accelerated motion, and let's say we are talking about the upward direction as the plus y direction and the downward direction as minus y direction. And using y instead of x, we would get the following equations. Velocity as a function of time would be v0 plus at. Now we know that free fall motion is uniform acceleration. It's uniformly accelerated in the downward direction. Right? So based on the sign convention we've adopted, we have to use we know that the acceleration is going to be negative. So we call that as negative of some constant g. Okay, so a is minus g here. So we can replace a by minus g in all in all the equations. This would be the first equation. The second equation would be delta y instead of delta x. Delta y is v0t plus half at square, right? Again, instead of half a, I would write minus half g because a is minus g. That's the second equation. And the third equation would be v square is v0 square minus 2g delta y. And the fourth equation can be the same if you want to use it. There will be no change. But, the graphs, the acceleration versus time graph would look like this, where this value is minus g. The velocity versus time graph, assuming a particle is thrown upward with some initial velocity that's directed upward. So we start out with a positive initial velocity, but then we know it's a linear function whose slope should be negative minus g. So it's going to fall like that, right, with a constant slope. So here the velocity is positive, initial velocity is positive. Eventually the particle keeps going up, comes instantaneously to rest, and then it starts falling down, so its velocity becomes negative. But the acceleration throughout is minus g. And if we were to plot the position versus time graph, y versus t, uh, because now the coefficient of t squared is negative, this is going to be a parabola that opens downward instead of upward. So let's say my initial position is 0. So in that case, my delta y would be the same as y because the initial y position is 0. So it's going to be a parabola that opens downward like that. So when the velocity is instantaneously at rest at the maximum height, you can see that maximum height appears here, and then it falls back down to the initial height from which it was launched. Okay, so that is this how it applies specifically to free fall motion. Any questions on all this? This basically covers most of the theory that's required for 1D kinematics. Sir, does the fourth equation assume non-uniform acceleration? No, no. We have assumed uniform acceleration everywhere. These equations apply only for uniform acceleration. They do not apply for non-uniform acceleration. So even in the derivation of the fourth equation, I have assumed delta x to be this quadratic function of time, which happens only with uniform acceleration. So in non-uniform acceleration, this result would not be true. And you can actually come up with examples, right? Imagine a car that is at rest for a very long time, and then suddenly in the last few seconds, it just accelerates to a really high speed. Okay. So for most of its time, it was at zero speed. So the you know the initial speed is going to be 0, and maybe it accelerated to a high value only in the last 1 or 2 seconds, right? Maybe it's a Tesla or some car that can accelerate to 30, 40 miles per hour within a couple of seconds. So that would be the final velocity. But the average of initial and final would be something like 20 meters per second or something, or sorry, 20 miles per hour or something, which uh, which is clearly not the average, because the average over time should be really close to 0, since for maybe several hours it was just at rest, and only in the last 2 or 3 seconds it accelerated to a high value. So that's not uniform acceleration, because the acceleration was 0 for several hours, and then in the last few seconds it attained some positive value. The average velocity cannot be equated to the average of the initial and final in such scenarios, only where there's uniform acceleration. Right, in that scenario which I just talked about, the average velocity should have been something almost 0, because for almost all the time it was at uh, 0 velocity. So um a couple of common problems that you should know how to solve is um, this one, for example. If you throw a ball straight up with initial speed v0, what is the time of flight? How long does the ball stay in air before it comes back to your hand? So you're throwing it vertically up. This is called the time of flight. So how would we solve this? What is the time of flight? Eventually, in this chapter, to solve problems, um, you have to fall back on the equations of motion if you solve them algebraically, or you have to fall back on the graphs of xt, vt, and at if you want to solve them geometrically. So here it seems pretty clear that this is an algebraic problem, which means you have to pick one of those three equations to to solve this problem. What you are given is the initial speed v0, and even if it's not mentioned, you can assume that you're given the acceleration due to gravity, which is always going to be minus g. And by the way, you can measure g um, once you see that it's free fall motion. Sorry, once you see that free fall motion is uniformly accelerated, you can set up precise measurements to find out, how exactly did delta x change with time, right? This experiment by Galileo that I talked about, he didn't measure g, he just determined that it's uniform acceleration. But if you want to measure g, which somebody did shortly after Galileo, um, you can set up an experiment with initial velocity 0 and then see how the displacement really changes with time. So after 1 second, where is it? Well, that value should be half a, and so you can get a from there, the magnitude of a from there. Or you can plot it for several seconds and then come up with a more accurate parabola that passes through all those points or close to all those points, and then based on the equation of the parabola, I can get a. So the assumption here is that we know what g is because that can be measured through experiments. And even if they are not given it to you, you can assume it in 1D free fall kinematics. So V0 is given, G is given, and we want to find out time. So the way to pick the right equation is there an equation that uh, has only these three quantities? Oh, actually, how long does it take to return to your hand? Return to your hand means um, your or delta x or delta y, if you want to call it delta y, that is also given to be 0. Right? These are the three quantities that are given, and you need t. So is there an equation that has exactly these four quantities? Well, yes, the second equation of motion has this. Delta y is v0t minus half gt square. Right? That's the equation that connects exactly these four quantities. So delta y is 0. This means t times v0 minus half gt is 0. So this means either t is 0 or v0 is half gt. So one of the solutions is t equal to 0, which we already know because if it's launched upward with initial speed v0, it's obviously in my hand. So there's no displacement so far at that point. So this is something we'll ignore, right? That's the trivial, that's just the initial condition. V0 is half gt. So after some time, namely t is equal to 2v0 by g, we are again going to get delta y to be 0. So delta y was 0 at the very beginning, and then it's also 0 uh, after the time equal to 2v0 by g. So this time of flight is something that is commonly used. Now, in the graph here, this is the time we are talking about. The time after which it comes back into your hand. 2v0 by g. So that makes it part E being correct. Okay, question here on the chats. Can we not assume that the final velocity will be 0 as the ball returns back to our hand? In that case, can we not use first equation of motion? if you know what the final velocity will be, then you can use the first equation. The problem is, in the first equation of motion, we have this, right? Now, I don't know what v is, right? That's not given to us. So it's hard to use it for that reason. Now, if you already know that, well, it's going to come back with the same speed, but in the opposite direction, then yes, you could set v to be minus v0, and you could get t is equal to 2v0 by g from there as well. But that is something which we can, instead of assuming that, we can prove it, right? We can prove it because once you have the time of flight like this, then we can find out after this time what will be the final velocity. It will be v0 minus gt. So that's v0 minus g times this time of flight, right? G and g cancel. So we get minus v0. So that's something which follows from the time of flight rather than something uh, we assume. Of course, now that you know that it's going to come back at the same speed, then you can use it for future problems. Okay, you can use the fact that it's going to come back at the same speed in future problems once you know that in reality this is how things are, neglecting air resistance. Likewise, the time of flight, you can use this formula in future problems once you have derived them. What about the maximum height? That's the other thing. The maximum height to which it rises. What is that? What is the maximum height to which the ball will rise? Right? Same conditions, right? We are given V0. We don't care about time right now. We're given V0, maximum height to which it rises. That means we are given V final also. V final is going to be 0, right? Because at the point where it's at its maximum height, it is instantaneously at rest, right? And you can see that from this graph. At its maximum height, we call this a maxima. This is called a maxima in calculus. The slope is 0. The slope is 0. What is the slope of the position versus time graph? That's the instantaneous velocity. So the instantaneous velocity is 0 here. That is something we know if the height is maxima. So the instantaneous velocity is 0. That is also given. And we are given, of course, always implicitly that the acceleration is minus g. And we want to find out what the displacement is. Which equation connects these four quantities? There's no time in this. Because there's no time in this, we can pick the third equation here to connect those four quantities. So v square, v final squared. So we'll work with this equation. 0 squared is v0 squared minus 2g times delta y. And this gives us 2g delta y is v0 square. So delta y is v0 square over 2g. This is the maximum height. v0 square by 2g. So I can go back to that graph and say, well, I know what this value is. This is going to be v0 square over 2g. Moreover, if it's coming back to my hand, I also know that this final value of the velocity will be minus v0. Any questions on what we've done here? All right, so let's do this one. We have two masses, two different masses that are fired directly upward with the same speed 2v. The first mass is fired upward with speed v. Second ball is fired upward with speed 2v. What's the ratio of the maximum height of ball 2 to the maximum height of ball 1? Well, you can just use the result we have. I mean, in 1D kinematics, to speed things up, it helps to remember some of these intermediate results, right? That we got. For example, that the ball is going to come back at the same speed with which we threw it up. The time of flight, total time of flight will be 2v0 by g. The maximum height will be v0 square by 2g. So if you have these in your mind and you're convinced, right? Of course, I'm not advocating memorization uh, of these without understanding of where they came from. But once you understand them, then to develop fluency, you can store them as uh, intermediate, as results that you know how to get to and directly use them. So v0 square by 2g is the maximum height. Uh, the other thing you have to use here is that the fact that these two masses are different is actually irrelevant, because we saw earlier that when you have free fall motion, when you have different masses, they cannot have different um, different natural speeds. They will both accelerate in the same way. So the acceleration for both masses will be minus g. So in that sense, because the acceleration is the same, uh, the masses are not going to figure in any of these. They don't figure in any of these equations, right? The equations of motion. They don't figure in any of them. They don't figure in any of these equations. So the fact that the same set of equations apply to both masses is something you have to first, be clear about in your mind. So ignore the fact that the masses are different. All that you know is the first ball is thrown upward with a speed v, second ball is thrown upward with a speed 2v. All right, so this is the conceptual piece here. They sometimes give you all this information, and some of that is just meant to detract people who don't have a clear conceptual understanding that irrespective of what mass you pick, the acceleration is going to be the same. The motion, free fall motion is going to be the same. Doesn't depend on the mass unless you bring in, air resistance and those factors, which we are not looking at in 1D kinematics. We also know that the maximum value of the height is v0 square by 2g, right? So that means the ratio of h max for ball 2 divided by h max for ball 1 is going to be, this ratio for ball 2 divided by this ratio for ball 1. So 2g is a common thing for both. So we can neglect it. So it just becomes the ratio of v0 square. v0 square for ball 2 divided by v0 square for ball 1. What's the initial velocity of ball 2? It's 2v. What's the initial velocity of ball 1? It's v. So this becomes 4 to 1. That makes choice B correct. So a ball that's thrown with twice the velocity is going to rise to a height that is 4 times as much as the other ball. How about this? Instead of vertical motion now, we have horizontal motion. Two cars with initial speeds of 2v and v, they lock their brakes and skid to a stop. Assume that the deceleration while skidding is independent of the speed. In other words, the deceleration is constant. Actually, you can ask the same question in the following way. You are driving along a highway at a speed v and you slam your brakes, you come to a halt after a certain distance, right? Skid to a halt after a certain distance. Skid means you're actually, the car is slipping on the road and it comes to a halt. What if you are going at double the speed? After how much distance would you come to a halt? What's the ratio of the two distances? So once again, what's given is initial speed, right? V0 is given. And you know that it comes to a halt. So you know that V final is given. Now the deceleration, the negative acceleration. Why negative? Because acceleration, when skidding, the acceleration is opposite to the velocity. So we can call it deceleration. Acceleration in the opposite direction as velocity. That quantity is not given to us, but we know it's the same for both cars. Okay, it's the same for both cars. So in a sense, we can assume that A is given to be something that's the same for both cars. Finally, if we have to take the ratio, that variable shall hopefully disappear. And what we want to find is the displacement, which is the same as distance because the cars are not making a U-turn. The cars are not making a U-turn here, so distance is the same as displacement. So which equation connects these quantities? Again, it's the third equation. V square is equal to V0 square. So let's say the acceleration is minus some quantity. I don't want to call it minus g. Let's call it minus, well, d sounds like distance. Uh, let's call it minus a. Okay, so it's going to be minus, so it's plus twice a times delta x, but instead of plus, I'm going to put a minus here and delta x is here, same, but v square is given to be 0. So the skidding distance delta x is going to be v0 square by 2a. Notice that this is similar to what happens in free fall motion. Obviously, the ball that's thrown up is not skidding to a stop, comes instantaneously at rest and then comes back. But here, what's happening is analogous to what happens in free fall motion when you throw a ball up and it starts decelerating and comes to a halt. So notice that this formula is parallel to the formula for the maximum height in vertical motion. Okay, so if the acceleration is same for both the cars, or the magnitude of the deceleration is the same for both the cars, the only difference is in their speeds, then the ratio, so the ratio of delta x um, is going to be the same as the ratio of their initial velocity squared, which is again 4 to 1. So in other words, if you double your speed at which you're driving, then and if you slam on the brakes and you skid, you're actually going to go 4 times as far before you come to a halt, which signifies the danger of overspeeding, right? Every time you overspeed by a certain amount, uh, if you slam on your brakes, you're, you know, you're going to go 4 times as far as someone, where you would stop if your speed was half. Okay. Um, so let's do one. Let's see how many problems do I have here. Okay, I just have one more. So let's just do this and then stop. You start from rest and you accelerate with a given constant acceleration for a given distance. Again, in a single direction, so no U-turns. Distance, same as displacement. Okay. If you repeat the process with twice the acceleration, then what will be the time required to travel the same distance? All right, so what is given? You're given that you're starting from rest. Again, we are comparing two scenarios here. So even if the values are not given, what matters is whether the variables, acceleration, all, whether they are the same across both scenarios or not. If they are the same, then you can assume them as being given. Okay, so the accelerations are also connected. We know the accelerations are connected because one is twice that of the other. So information about acceleration is given. Information about the distance or the displacement, because there are no U-turns, distance is same as displacement. This is also given because we are going the same distance in both scenarios. What we need to find is how does this affect the time? So which equation connects V0, A, delta x, and t? That's the second equation of motion. So delta x is V0t plus half at square. This is what we want to use to connect all these variables. So again, there are two scenarios. So I'll just call the distance as d. V0 is 0. So in the first scenario, we have this. In the second scenario, we are going the same distance, but we are going with twice the acceleration. So how will the time required, let's call this t2, how will the time required be connected to the earlier time? So, well, we can take just the ratio of these two equations, right? So let's say we take the first equation and let's say we take the second equation and we divide it by the first equation. So on the left hand side, we'll get 1. On the right hand side, we will get 2a divided by a, which is 2. 2 times t2 squared by t squared, right? So that means t2 by t is half. Sorry, t2 by t squared is half. So that means the ratio of the times is going to be 1 divided by the square root of 2. So the time required in the second scenario decreases by a factor of square root of 2. So remember that all of these equations apply only when the acceleration is known to be constant. Otherwise, we cannot apply these equations of motion. And by default, they apply even for uniform velocity motion because their acceleration is 0. So if acceleration is 0, then we get much simpler forms of the same equation, right? If acceleration is 0, that means my velocity is constant. If a is 0, vt is always v0. What does the second equation give me? That means my position at any time is the initial position plus v0t, right? If I put a equal to 0, this term goes away. That means my delta x is always v0 times t. So in other words, displacement is velocity times time, right? And that's your trivial distance is equal to speed by time equation. We're only talking about one direction, it's uniform velocity. So displacement and distance are then interchangeable. And the third equation is not going to give us anything new because when a is 0, it's just saying v square is v0 square. Well, that's, we already know that. It's uniform velocity. And likewise, this will just say average velocity is the same as whatever that uniform velocity is. Because this will be double that divided by 2, same as that constant velocity. All right, any questions? Otherwise, we will stop now. Did this class help? Did it add any new information to you? If you could just put that in the chat box, or is it just a repetition of what you already know? Is this helping? Yeah, I'm asking because when I asked earlier if, I think after an hour when I asked about derivatives, seemed like those who are attending here, not many of you, but 8 to 10 of you, you kind of indicated that you already know this. Can you again tell why distance and displacement are at times synonymously used? Well, distance and displacement are um, synonymously used if there are no U-turns. Right? Suppose you have motion in which the particle never turns around. So it starts here and it ends there. And we don't know how it how it moved, it could have moved at very different velocities during its motion. But the point is, it never made a U-turn. So in that case, my displacement would be delta x, x final minus x initial, right? Basically just the length of this arrow. And my distance, which is the length of the path traveled, is also the length of that arrow, right? Because I never turned around, so I could never exceed the length of that arrow. So it's the same as the displacement, at least the magnitude of the displacement. If the particle was moving in the opposite direction, the displacement would have had a negative sign, but the distance would have still been the same. Okay, any other questions? Helpful revision. Okay. And we still have things to discuss in this chapter. Uh, I haven't talked about integration and a few other graphs, Vx, Ax graphs, which we'll take up in the following sessions. All right. Thank you all. We can stop here if there are no more questions.